Good afternoon, everyone. I am Vinay Kumar, and today I am going to tell you about Earth observation sensors, which are acquiring remote sensing data, and which kind of platforms are useful for acquiring Earth observation or remote sensing data. Now, before I'll start to that, I would like to tell few basic things like every human being, that equipped with some of the sensors. Out of those sensors, some sensors are working as remote sensing sensors, like your eyes, ears, and your nose. And these sensors are placed properly on your head so that it can acquire data properly. Similarly, if you remember, like you must have processed your digital images, and if you zoom your digital image, it will be going to get pixelated, and that pixelated information, and you are able to do the modification or do the changes to that digital image, because that digital image is nothing but some numbers are there. So these two things are how utilized in your remote sensing or with this Earth observation sensors and platforms that I am going to explain in my slide. So you might have seen this particular that how the remote sensing process is taking place. In this slide, you are seeing that energy source is there, which is sun here, and sun is sending some energy, that is your incident energy, and that incident energy when reaching to the target or your earth surface, some is getting absorbed, some is getting transmitted, and some are getting reflected back to the sensor if it is passive sensor. But if it is active sensor, then sensor itself is giving its own source of illumination, and then reflected energy is going back to the sensor. Now whatever data or getting reflected from the earth surface, that data is converted to digital number and converted to electronic signal while transferring it to the ground receiving antenna placed in earth. So in case of India, we are having 4 ground receiving antennas at Sadnagar, NRSC Sadnagar. So in this particular ground receiving antenna, you see it is written as ground receiving and processing station. So while acquiring the data, you can see in between sun and your earth surface, atmosphere is also there. So whatever energy we are expecting to receive from sun is not coming because of that atmospheric error. Secondly, your sensor is also a electronic and mechanical device. So because of that also sometimes some detector failure or some issues with the sensor, we are not able to receive some of the data sets. So due to that, some errors are getting introduced. So these errors are getting rectified in this ground processing station, and then we are giving it to user. Now you are seeing here that some SATCOM is written over there. So this is actually communication satellite which is required when you suppose you require data urgently, then what you have, and your ground receiving antenna is not in the range of this particular satellite sensor, then what it is doing, it is transferring that data to some nearby communication satellite, and whenever that communication satellite is near to the range of ground receiving antenna, it is sending the data in form of electronic signal, and that this signal is converted to two-dimensional image. And as I told to you that we have to do certain pre-processing, we have to rectify certain errors. Those are maybe atmospheric errors, radiometric sensor induced errors, or maybe geometric errors. So these errors you have to rectify it, and then we are giving it to the various users, and then the users analyzes that particular data according to their usefulness, like agriculture scientists for agriculture application, forestry application, or water application. For various applications, they are generating various kinds of maps. Now coming to definition of sensors and platforms. So sensors and platforms are what? Sensors and platforms are used to create image data of the earth. And sensors are what? Which are recording device that records electromagnetic energy. So for example, you can see remote sensing is what? Remote sensing is collecting data or acquiring data without without being in physical contact with the object, but it requires electromagnetic energy. So if you are seeing my lecture, you can see the lights are properly illuminating me. That's why the display is going properly. So it means whatever sensors are there, they are able to receive energy because of that electromagnetic energy present over there, which is reflecting from me. Now platforms are what? Platforms are carrier bed used to carry sensors. So I have given you three examples, like for human being that ears, eyes and nose are properly placed on our head so that we can acquire information. So platforms are something, some kind of carrier bed which are carrying the sensor to acquire the data of whole earth surface properly. Now, before I'll tell you about various kinds of sensors and platforms, I'll just try to tell you about the history of remote sensing. So before that first photograph acquisition, what was happened? That started with the invention of telescope. So telescope was invented by Hans Lippershey. So that telescope was introduced to astronomical purposes by Galileo, and that by using that telescope he started seeing the dark spot present on sun, and the craters on moon, and whatever objects which are revolving around Jupiter planet and the ring revolving around Saturn. Then after, in 1827, after the invention of camera, first photograph was taken. Then in 1858, first aerial photograph from a hot air balloon was taken by her. So you can see this by this way he have taken the photograph. So the photograph was taken for the Paris area, that is the capital of France. Then from 1861 to 1865, balloon photography used in American Civil War. So this was giving you the two-dimensional photograph of that area, and this was useful for monitoring the enemy troop movement. Then after that, in 1888, rocket cameras was launched, and in 1903, pigeon mounted cameras are patented. So you can see how the camera mounted in the pigeon. And if you'll see some of the photographs, you can Google also pigeon pigeon acquired photographs. So you can see the wings are also coming while collection of photograph by pigeon. Then in 1906, photograph from kite was taken, and then in 1914 and to 1945, after invention of aircraft, the plane mounted cameras are used in World War I and World War II. Then in 1956, U-2 spy planes was used, and after that the first satellite was launched in 1957, that was Sputnik 1 by USSR. Then in 1960, first meteorological satellite Tiros 1 was launched. And you know that in 1967, first remote sensing satellite program was started, and then in 1972, that Earth Resource Technology satellite launched, that was renamed as Landsat 1 after the launch of Landsat series satellite. So you can see the satellite image of Landsat 1 of 23rd July 1973, that how the image was appearing. After that, just let me tell you about three category of platforms: ground-based, airborne and spaceborne. And why we went for spaceborne data acquisition, you can see the synoptic coverage of that different types of platforms. So satellite with 800 kilometer altitude, you can see we are able to cover a larger area. Then from aircraft with a 10 kilometer altitude, you can see the coverage is approximately 357 to 1956 kilometers. Sorry, 357 kilometers. After that, with the hot air balloon with 100 meter, that is around 35.7 kilometer, and with 10 meter altitude, we are able to cover 11.3 kilometers data. And with 1.6 meter, you can see that we are covering a very small area. So you can see ground-based, airborne and spaceborne platforms are there with various altitude. Normally, spaceborne platforms are actually used for acquiring data on a continuation basis, because once a satellite is launched, it will give you data till its lifetime. But aircraft, whenever you will launch you will fly the aircraft, at that time it will acquire the data, and you can use the data only when the aircraft lands. But for higher spatial resolution, you have to fly an aircraft. And ground-based sensors are actually useful for giving you proper details of Earth surface features, and whatever features you have acquired from satellite based platform or your aircraft platform, whether the data is proper or not. So for validation and calibration purposes, you have to use this ground based platform. So now ground based platforms are what, which is useful for recording detailed information about the surface, which is compared with information collected from aircraft or satellite sensors. So normally the ground-based platforms are maybe your truck, high-rise building, crane, scaffolding. You can use that and you can put your instrument to that and you can acquire the data. And for proper characterization, you can see for proper characterization of the target, you require this ground based, and you can compare with your aircraft and satellite sensors data, acquired data with using aircraft or satellite sensors. Now airborne platforms are sometimes your stable wing aircraft or helicopters also can be used for acquisition of data. They are actually, I already told to you, they are flying with a lower altitude, so they are giving you high spatial information. So I am going to tell you what spatial information means in my upcoming slide. And whenever suppose you require data urgently, then you can fly aircraft anytime and you can acquire data and you can process the data after landing the aircraft. So why this kind of platform started? You can think of, as I told you, balloon or kite and pigeon. They are we are mounting cameras on that also, but they are only giving you JPEG information, but the altitude was not constant. But in case of your aircraft, the altitude is constant and you can fly, get the data with a proper information. But some limitations are also there with the aircraft. This is going to be a very costly operation, because whenever you have to fly a aircraft and you require a data, then flying an aircraft and taking permission and all, so they are making the data acquisition costly. Secondly, the limitation is of the data processing. You can process the data only when the aircraft will land. Now coming to space-borne platforms, there are two types of space-borne platforms. One is space shuttle, that is named as manned spacecraft. So if using this, people can go to space, they can acquire the data and they can come back. And satellites are more commonly used in remote sensing purposes. So satellites are what? Satellites are objects which revolve around another object, in this case the Earth. So when Kepler started studying about the astronomical things like various types of features which are revolving around Jupiter, so he have given the name as satellite. Satellite is something like something is guarding that particular planet. So in our Earth's case, the moon is a natural satellite, whereas man-made satellites include those platforms launched for remote sensing, communication, and telemetry purposes. So you can see how the space shuttle looks like, and these are few examples of the satellites which are acquiring data from Earth's surface. Now coming to how satellite is revolving around your Earth's surface. So before that, you should know about, so the path followed by the satellite is called as orbit. So you can see, suppose this is your Earth, which is revolving, which is rotating from west to east, and satellite is revolving either maybe from north pole to south pole or with the equatorial plane. So that is also called as path. The coverage of that particular area is called as swath, that I am going to explain in my upcoming slide. So the satellite moves as per Kepler's law. And what are the Kepler's law? So there are three Kepler's law. First law is the path followed by each planet is an ellipse with sun at one of the focus. So you can see this is the elliptical path, and one focus of that particular ellipse is called as sun. So this is your major axis and this is the minor axis of this particular elliptical orbit. So sometimes you can see whatever satellite is revolving around Earth's surface, they are also following that elliptical path, and they are even circular also. So when eccentricity becomes 0, then the ellipse becomes circle. So now coming to the second law. The line joining to the planet to sun sweeps out equal areas in equal time. Means whatever area is covered by, suppose in this particular image you can see, if suppose earth is revolving around sun by following this elliptical path, so whenever it is acquiring covering this particular area, suppose this area is A1 and it is covered by T1 time, and this particular area is suppose A2 and it is covered by T2 time, so the product is always going to be constant for each case. Now coming to third law, the square of the period of the planet is proportional to the cube of semi-major axis. So square of time period means time. What is time period? Time period means to complete one full revolution by satellite, that is called as time period, and square of that time period is proportional to the semi-major axis of that particular from earth to sun. Suppose this is that ellipse you are seeing, so this is your semi-major axis, so that will be the time period, square of time period is proportional to the cube of semi-major axis. So each and every satellite whatever is revolving around Earth's surface, they are following the Kepler's law. Now coming to satellite orbital characteristics. So these are the orbital characteristics of various satellites which is required, which is there whenever satellite is launched. So altitude is what? Altitude is the height of that particular platform with the mean sea level of the Earth's surface. And inclination angle, this is one of the very important thing, and altitude is also one of the important factor. Just let me tell you, depending on altitude, if altitude is larger, your spatial resolution is also dependent to that. So I'm going to tell you how the spatial resolution is affected in my upcoming slides. Now coming to inclination angle. Inclination angle is, suppose satellite is revolving from this to this angle and your equatorial plane is like this. So whatever angle is made by the orbital plane to the equatorial plane, that is called as inclination angle. And this is going to be very important factor, as suppose this is your earth surface and suppose this is your inclination angle. So what is going to happen, suppose it is making 60-degree angle. So what will happen, up to plus 60-degree latitude to minus 60-degree latitude, it is going to cover the earth surface, and beyond 60-degree and above or below 60-degree, it is not going to acquire any data. So we have to launch such satellites so that we can, means we have to launch satellite in such a way that it can acquire whole Earth's data. Then period, I already told to you, to complete one whole Earth revolution, that is called as time period. Now coming to repeat cycle. Repeat cycle means, as I have given you one example, that satellite is, Earth is continuously rotating from west to east and satellite is revolving from North Pole to South Pole. So suppose one revolution is completed, till that satellite is also rotating. So one revolution is completed, after some days the same orbital pass is made by that satellite is called as repeat cycle. Then coming to swath. Swath is something like, you suppose you are using a camera and you are taking a photograph. So you know that it is able to see to a certain extent. So that particular width covered by that satellite is called as swath. So you can see this particular image. Suppose this is the satellite, this is the sensor placed in this satellite. So the width covered by this particular platform, this is called as swath width. Now coming to ascending pass and descending pass. This is very important factor for different types of sensors. Suppose the data, suppose the sensor is requiring electromagnetic energy, or if they are passive sensors, then they can use some descent pass while acquisition of data. Like as I told you, Earth is rotating continuously, Sun is fixed at some position. So suppose Sun is fixed at this position and Earth is continuously rotating and seeing the same area, seeing the Earth's surface. Now satellite is revolving from North Pole to South Pole. So whenever it is moving from North Pole to South Pole, that is called as descending pass, and from South Pole to North Pole it is coming, that is called as ascending pass. So whenever it is going from North Pole to South Pole, during that Sun is looking to that area. So during descending pass, most of your passive remote sensing sensors are working, except your thermal remote sensing sensor. Because thermal remote sensing sensors acquires data during night also, because whatever sensors, whatever energy is gets absorbed during daytime, it start emitting at night time also. So that is getting acquired by thermal sensor during night time also. So during ascending pass also they can acquire data. Now coming to perigee and apogee. Perigee, you can see this is the earth surface with earth which is rotating from west to east. So suppose satellite is revolving, either it may be from north pole to south pole or it may be in the equator. So whatever point, when suppose satellite is having some point which is closest to the earth surface in that particular orbit, that is called as perigee, and the farthest point is called as apogee. So this is not that far, but to explain that what is perigee and apogee, I have explained. I have shown this through that through this image. Now coming to category of two types of satellites. So as I told you, orbits, I have told you about orbit. Orbit is what? Path followed by the satellite. So they are actually categorized into three types: polar, equatorial, and inclined. Polar satellite, whenever, as I told you, inclination angle is what? The angle which is making with the equatorial plane. So suppose if it is making 90 degree, it means it is moving from north pole to south pole, that is 90-degree angle. So that is called as polar satellites. And whenever it is making 0 degree or 180 degree, that is called as equatorial, or you can say, I will tell you about but that is called as equatorial orbit. And whenever it is making any angle, it may be from 0 to 90 degree or it may be from 90 to 180 degree, they are called as prograde and retrograde orbits. Now on the basis of that, satellite orbits are also categorized into two types, that is geostationary and sun synchronous satellite. So you must have heard about two types of launch vehicles also, GSLV and PSLV. PSLV is your polar satellite launch vehicle, GSLV is your geosynchronous satellite launch vehicle. So geosynchronous, why it is called as geosynchronous? Geosynchronous means it is synchronized with the velocity of Earth. So suppose it is rotating with the speed, Earth is rotating from west to east with some speed, and satellite is also revolving as such that it appears that it is synchronized with Earth's surface. And sun synchronous satellite, why it is called as sun synchronous? As I told you, during descending pass only your remote sensing satellite is acquiring the data. So it should be synchronized with sun's energy. So sun is giving energy to the earth surface, and during descending pass it is acquiring the data. So now coming to this two category, geostationary satellite and sun synchronous satellite. Normally geostationary satellites are having altitude of 36,000 kilometers. But it's not necessary that it is 36,000 only. Some satellites are having 33,000, 34,000, 35,000 kilometers also. But most of the satellites are having altitude of this 36,000. Orbital inclination, as I told to you, that it should follow in the equatorial plane. So normally the inclination angle should be 0 degree. And period is to complete one whole satellite revolution to the Earth surface, that takes around 24 hours. Now, for global coverage, it requires several geostationary satellites in orbits at different latitudes. Why we are saying this? Because see, as I told to you, that it appears it is fixed at some position, it is all looking to the same area. So what about the remaining portion of the Earth surface? So that's why we require several geostationary satellites so that we can acquire data for whole Earth surface. So Earth is continuously rotating. Suppose one satellite is placed here, it is seeing this area. Then for other portion, we have launched a satellite here so that it can cover whole Earth surface. So this is good for repetitive observation for spatially detailed data. Why? As I told to you that altitude is one of the important factors which is affecting the spatial resolution. And here I have written large distortions at high altitudes. Why I have written that? Because you know that Earth is not flat. So at higher altitude Earth is curved. So in this particular portion we are not getting any distortions, but when Earth is curved we are getting some distortions. So that's why we are getting distortions at higher latitudes with your geostationary satellite images. Now normally all the geostationary satellites are west to east orbiting, and mainly useful for communication, meteorological, and weather forecasting purposes. Some examples are your GOES, Meteosat, and INSAT satellites. Now, sun synchronous satellite. Normally, sun synchronous satellites are having lower altitudes. You can see compared to this, it's very low. So some satellites are having 900 kilometers, some are having 600 kilometers also. Now, orbital inclination is 98.7 degree. This is just one example of some sun synchronous satellite. So why you can see it is near to pole only, 98.7 degree, so that we can acquire whole Earth surface. And orbital period is approximately 90 minutes. So normally you can calculate by yourself also by using simple equation mv square by r is equal to mg. Then you can calculate if altitude of satellite is given, then you can calculate your time period also. It is normally called as sun synchronous, near polar, near circular. And satellite orbit is fixed in space, basically north to south, and Earth rotates beneath it. So I have given you example that Earth is rotating like this and satellite is revolving from North Pole to South Pole. So because of rotation of Earth and revolution of the satellite, whole Earth data gets acquired. And normally it crosses the equator at local time, maybe 9 a.m., 10 a.m., 10:30 a.m. Satellite orbital plane is near polar and the altitude is such that satellite passes each place at same local sun time. So as I told to you, sun is always looking to the earth surface and earth is rotating and satellite is revolving. So during descending pass, it is acquiring the data. So at same local sun time, it is acquiring the earth surface images. So normally it covers entire globe, and the data satellites which are used as sun synchronous satellite, that is Landsat, Spot, NOAA, and IRS. IRS are Indian remote series satellites, the remote sensing series satellites. Now, as I told to you, satellites orbit because of the revolution from north to south pole and the rotation of Earth from west to east work together to allow complete coverage of the Earth's surface after it has completed one complete cycle of orbit. So you can see because of this revolution of the satellite and rotation of your Earth surface, whole Earth data gets acquired. Now just I'll add some more point here. Actually, whatever sensors are there which are acquiring data, they are acquiring data on a continuation basis. So what we have to do, we have to divide that particular images in certain scenes or certain frames. So what we are doing, we are making parallel lines to equator and then we are dividing that particular, and whatever, suppose this is the earth surface and satellite is revolving, suppose it is covering this particular portion. So what is happening, parallel to equator, we are dividing that into some path and route. Suppose this is acquired till that satellite is rotated, earth is rotated, again satellite is coming, one orbital pass again, then again some orbital pass is made. So whatever orbital pass is made and parallel to equatorial line, we have drawn some lines so that we can create some scenes or frames, and that we are giving it to user. So that is called as path and route. So using that, you can suppose you require data of certain area. So using path and row, you will be able to tell that how much which path and row data is required for your particular study area. Now coming to sensors. Normally, you know that sensors are categorized on the basis of energy source. So if energy source is external, that is called as passive remote sensing. That is also called as optical remote sensing whenever we are not using the longer wavelength region. And active remote sensing sensors are those which are having own source of illumination. So you can see in this particular image, sun's energy is coming and reflected energy is going back to the sensor. In this particular case, you can see sensor itself is sending the energy and backscattered energy is going to the sensor. So microwave remote sensing is one of the example of your active remote sensing. And these are some of the images of various Indian remote sensing sensor. This is the panchromatic camera. These are some of list 1 and list 2 sensor images. So you can see how the sensors are appearing remote sensing sensors are appearing. Now those sensors are also categorized into two types, imaging and non-imaging sensors. Imaging sensors are also categorized into that sensors, passive sensors and active sensors. So normal photographic camera is passive sensors, but whenever you are using the photographic camera with flash, they comes under active sensor also. Then coming to optical scanner, so they are categorized into two types, across track and along track scanner. So this I am going to tell you in more detail what is across track scanner and what is along track scanner and how they are acquiring the data. Then thermal scanner, as I told to you that thermal remote sensing sensors are actually acquiring the emitted energy. So they are actually useful for detecting coal fire or identifying the fumes, fire inside the volcano. Then coming to active sensors, so they are also categorized into two types, radar and lidar. Lidar is actually normally using infrared range, and radar sensor, this particular things you will be learning in more detail. Radar is radio detection and ranging, that is your SAR sensor. So that is actually useful whenever you require data from those areas which are always covered with clouds and rain, because these sensors are having capability to penetrate through cloud also and through rain to some extent. Then coming to non-imaging sensors, so I have directly written spectroradiometer, but spectrometer and radiometers are also there. Spectrometers are the instrument which are able to means for different features, means the features which behave differently with different wavelength, or something like suppose you are using a prism, and whenever you are passing a monochromatic light, you are able to distribute the electromagnetic wave spectrum. So for each particular wavelength, how the features are behaving, that you can measure through the spectrometer. And radiometer is what, for a particular wavelength, what intensity value is coming or what reflected energy is received, that is called as radiometer. The combination of both the two is called as spectroradiometer. So you might have learnt about spectral reflectance curve in your previous lecture. So spectral reflectance curve can be measured with the help of spectroradiometer for a particular object. Now coming to active sensors, laser distance meter, laser water depth meter, microwave altimeter. So they are useful for giving you the distance kind of thing, because laser distance meter, that is working with it, you are targeting a laser and whatever energy is received back by the sensor, so by that way you can calculate the distance. So similarly, laser water depth meter is also working. Microwave altimeter is useful for measuring the sea depth and sea waves also, sea wave height. Actually this is the image of spectroradiometer, so you can see how the spectroradiometer looks like. Now coming to a cross-track multispectral scanning. So most of your remote sensing sensors are using two types of multispectral scanning. Either it may be a cross-track or a long track. So what is a cross-track multispectral scanner? The other name of a cross-track multispectral scanner is whisk broom scanner. Now why it is called as whisk broom scanner? In this particular whisk broom scanner, you are having a rotating scan mirror. So in this rotating scan mirror, what is actually happening? Suppose this is the swath of this particular means this particular portion have to be covered by your sensor. So in this particular thing, you are having a rotating scan mirror. So rotating scan mirror is scanning the data, scanning the area pixel by pixel and moving across the swath. So that's why it is called as whisk broom, because we are brooming across the track and moving in further direction. Because satellite is having velocity, satellite is moving in such a way, satellite is moving continuously and sensor have to scan data like this. So it is having a rotating scan mirror, it can collect, it is collecting data pixel by pixel. But the disadvantage of this particular whisk broom scanner is what? In this particular case, whenever that scanner is working, so that scanner have to move very fast because satellite is having some motion. So when it started, it have to gain some velocity and it have to stop. But when it reaches to the extreme, we are satellite is also having motion, so some pixel shift also is coming into picture. So those errors we have to rectify before giving it to users. So normally data are collected within an arc below the system, typically of some 90 degrees to 120 degrees. So you can see this particular area, this particular angle, this is called as field of view. Normally it varies from 90 to 120 degrees, and whatever area is getting covered by that particular small instant, that is called as instantaneous field of view, which I am going to tell you in more detail in my upcoming slide. Then this is please remember, for each particular wavelength, suppose you are having a multispectral sensor with suppose 5 bands: blue, green, red, near infrared, or short wave infrared. For those particular bands, for all the detectors are different. So for different bands, different detectors are there which are acquiring the data. Now multispectral scanner and thematic mapper of Landsat and AVHRR of NOAA are the examples of whisk broom scanners. Even recently launched operational land imager of Landsat 8 satellite is also using this whisk broom technology. Because the advantage in this particular case, once I'll tell you the along track multispectral scanner, then I'll be telling you about what is the advantage of this whisk broom scanner. Now coming to along track multispectral scanner, this is called as push broom scanning. So as I told to you that single detector is there for suppose blue band, green band, red band, near infrared. For blue band also single detector is there, green band also single detector is there. But in case of along track multispectral scanner, you are having thousands of detectors placed in a linear array. So in this particular thing, you don't have any rotating scan mirror kind of thing. So at the same instant when the data acquisition is taking place, if satellite is moving, so like this it is acquiring the data. So it is something like we are pushing the broom in further direction. So it is along the track moving and collecting the data. So it also scans Earth in a series of lines, but thousands of detectors are there. So suppose one linear array of detector is there for blue band, one linear array of detector is for green band, one linear array of detector is for red band. So like that you are having various linear array of detectors for collecting the data. Now I told to you this also use the forward motion of the platform to record successive scan lines and build up a two-dimensional image perpendicular to the flight direction. Normally it uses CCDs for collecting data, and linear image self-scanning and wide field sensor of iris series and high resolution visible of spot 1 are examples of push broom scanners. Now the advantage of this push broom scanners are what? At an instant you are collecting the data for whole swath. So what is happening? For a longer duration you are seeing the particular area, it means you are receiving more signal from the earth surface. So your resolution is also getting affected, means you are getting better detailed information in case of your along track multispectral scanner. But in case of whisk broom scanner, because you have to collect data pixel by pixel and it have to move also, so it have to move faster because it have to satellite is also moving further. That's why the time which the sensor is looking to the area is very small. So that's why we are thinking for higher spatial resolution we are thinking of push broom scanner. But the disadvantage of this along track scanner is what? Cross calibration of thousands of detectors are very difficult, because in that case you are having a single detector. So cross calibration you can do it very easily through your across track using your across track multispectral scanner. Now coming to resolution. So before I'll start with resolution, just let me tell you about, I told you digital image. So digital image, you must have done image interpretation, and you must have enhanced your images, you must have done manipulation with your images. So why you are able to do that? Because your digital image is nothing but some numbers are there. So that number you are able to change, but you cannot change anything with your hard copy images, because once it is printed, it will be, you can only interpret, you can identify the features from that, but you cannot make any changes to the hard copy images. Now resolution is what? Whenever you are zooming that digital image, what is happening? That digital image is getting pixelated, and the smallest unit of that digital image is called as pixel. Pixel is what? That picture element. The short form of that picture element is called as pixel. So that pixel size will tell you about the spatial information. And as I told to you in whisk broom or push broom scanner, that for different bands you are having different detectors. So you that is dependent on your spectral, means electromagnetic spectrum. Then coming to time, suppose you are acquiring some data for the same area, that is your temporal resolution. So just let me tell you what is resolution. Resolution is ability of the system to render the information at the smallest discretely separable quantity in terms of distance, that is related to your pixel size. Wavelength band, that is related to the number of bands or the bands present in your data sets. Then time means how frequently you are acquiring data for the same area. And radiation, the number present in that digital image, that radiometric value, that is actually playing an important role. So depending on that, it is categorized into four types: spatial, spectral, radiometric and temporal. Spatial resolution is a measure of discernible physical dimension of the surface from the image, that I told to you, size of the pixel. For example, in this case, just let me tell you, if suppose two objects are there which is 1 meter apart, okay, why it is written as smallest discrete separable quantity. Suppose two objects are there which is 1 meter apart, and if your pixel size is 30 meter, these two features will not be visible in your data. But if the same features are present and you are acquiring data with 50 centimeter resolution, these two features will appear in two different pixels. You are able to identify, and you will be able to see the features very clearly. Now coming to spectral, this is a measure of the width of the wavelength which is used to generate the image. Narrower the bandwidth, higher the spectral resolution. What does that mean? Means, if as I told to you, just remember first, you must have used black and white camera. Using black and white camera, you are able to see the features clearly, but the color informations are missing. But using your color camera, you are able to differentiate all the features with different colors. So why we are in this particular case, suppose you are using blue band camera, green band camera, red band camera, and you are generating different color composites, you are able to analyze the features more clearly. So what this bandwidth means, I am going to tell you in my further slide. Now coming to radiometric resolution is dependent on whatever energy you have received from the earth's surface. So suppose your energy label, whatever you are recording, if you have to differentiate the energy label, you have to give some radiometric values to that I am going to tell in my upcoming slide. Then coming to temporal, frequency of observation. I told to you that how repetitively you are acquiring the data for the same area with the same viewing geometry, that is your temporal resolution. So coming to spatial resolution, as I already told you, this is physical dimension on earth is recorded. It refers to the amount of detail that can be detected by a sensor. So suppose I am using a push broom scanner, this is the pixel size. So this is the detector size which is acquiring the data. This particular area, suppose this is making some solid angle. So whatever angle it is making, that is called as instantaneous field of view. So that instantaneous field of view you can calculate by using the detector dimension and your focal length. So instantaneous field of view is detector dimension upon focal length will be instantaneous field of view, and whenever you will multiply with your altitude, that will be called as ground resolution element or your spatial resolution. Means that size of that pixel can be calculated with that. So as I was telling you repeatedly, that height is playing a major role. So when you will multiply with altitude, so as I told you, 36,000 kilometer if you will multiply, so you can think of your spatial resolution is getting coarser. So please remember, larger the number means coarser the pixel size. It means the features which you want to discriminate, smallest difference also, you will not be able to discriminate through higher means coarser spatial resolution data, means larger number. And if you want to differentiate two features with a smaller distance, you require higher spatial resolution data. It means smaller number, like suppose 1 meter resolution. So by this way you can differentiate the feature. So altitude is very important for in case of your spatial resolution. So detailed mapping require higher spatial resolution data sets, means lower number, smaller number data sets. So you can see we started with actually 1 kilometer resolution to 1 meter spatial resolution. These are some of the Indian remote sensing satellite data sets. So you can see how the data sets are appearing with various resolution. I am going to tell you in more details. So for various application, what resolution is required? Like for meteorological purposes, cloud patterns, movement, water vapor analysis, 1 to 2 kilometers and 8 kilometers resolution is required. For oceanographic application, ocean color monitoring like chlorophyll, sediment map, yellow substance, sea surface temperature mapping, 300 to 1100 meter spatial resolution is required. And for land use mapping like crop monitoring, forest mapping, hydrological application, 20 to 30 meter resolution is required. For cartography and urban mapping, urban planning, higher spatial resolution, 2 to 6 meter resolution is sufficient. And for military surveillance, less than equal to 1 meter resolution is required. So 1 kilometer to 1 meter spatial resolution data sets are there. Now we are having sensors which is less than 1 meter, that is 31 centimeter resolution data sets are available from space. So 24 days to every 30 minutes repetitivity data sets are acquiring by satellites, and 1 million to cadastral, 1 million scale to cadastral level mapping can be done using this kind of satellite data sets. Now you can see information content versus spatial resolution. You can see this is ocean color monitor data with 360 meter. So for that we have taken the 4 by 4 kilometer square block, and we have seen the pixel area of the same area. So you can see we are not able to see any particular feature. But when we have used the 188 meter resolution data, some details are coming, but still we are not able to identify. With 72 meter list 1 sensor data, you can see some details are coming, but still it is very coarser. With list 2 sensor, the features are coming clearly. If you know image interpretation, you can identify the features, but still you are not able to discriminate features very clearly. With 23 meter, you can see the spatial details are very clear. And then with 5.8 meter resolution, you can see the features are very clear in compared to other previous images. Now coming to spectral resolution, as I told you, it describes the ability of sensor to define fine wavelength interval. This refers to the number of bands in the spectrum in which the instrument can take measurements. Higher spectral resolution, better ability to exploit differences in spectral signatures. So normally it is categorized in 3 types: panchromatic, multispectral and hyperspectral. Panchromatic is normally a single band camera which is using the wavelength range from visible to near infrared. Then multispectral, whenever you are further subdividing that visible to near infrared band on with more number of bands, blue, green, red, near infrared, short wave infrared, then they are called as multispectral. So number of bands are normally tens in this particular multispectral. And hyperspectral, which are giving you contiguous spectral information, normally it contains 100 to 200 spectral bands. So in this particular case, you can see we can generate true color and false color composite image using the multispectral information. And now coming to the spectral bandwidth, whatever I was talking about. So suppose if it is a single band data, so for single band data you will be getting a grayscale image. So it is covering an entire wavelength region, and then you are getting some reflectance value. Suppose you are categorizing blue band, green band and red band. So for that you are getting some reflectance value. So you can see here there are 3 sensors, Landsat 7 ETM plus, which is having I have used here 6 band here, not the thermal band. And in this particular EO1 LE I have used 9 band, and in this EO1 Hyperion, after correction and all, I have the data with 140 bands. So you can see here the spectral details are more clearer whenever we are moving towards more number of spectral bands. So if you want to discriminate species level features, then you can go for hyperspectral data. So I was talking about blue band, green band and red band. So in hyperspectral, even blue band is also categorized into more number of spectral bands, and using that you are able to discriminate all the features more clearly. And using that you can generate different true color and false color composite. So why we are going for false color and true color, you know already that using standard false color composite, whatever features are not clearly visible through true color, we can interpret through this very clearly. And vegetation features are giving very high reflectance in near infrared range, then that's why we are using standard false color composite images. Now coming to radiometric resolution. Radiometric resolution, as I told to you, that whatever reflectance values are there, they are giving you the actual information content. So normally your sensor is receiving reflected energy, that is in form of radiance, and depending upon radiometric resolution it is converted to digital number. Now actually what is happening, suppose two different features are there, water and vegetation, so it will give you different reflected energy, you will be able to discriminate. Now suppose there are two similar kind of features present into that, means very small difference in the energy whatever we are receiving, then we are not able to distinguish if your radiometric resolution is going to be lower. So your radiometric resolution of your imaging system is what? It's an ability to discriminate very slight difference or very small amount of energy level recorded by the sensor. So finer the radiometric resolution of a sensor, the more sensitive it is to detecting smaller difference in reflected or emitted energy. So I will show it with some of the images. You can see normally radiometric resolution is dependent upon the number of bits. If more the number of bits will be, more the number of gray labels are there. So you can see if this is the number of bits 1 2 3 4 5, so for that you can calculate the number of gray labels. So if it is 1 bit data, you have 2 gray labels from 0 to 1. If you have 4 bit data, you can generate 16 colors which is ranging from 0 to 15. For 8 bit data, you have 256 gray labels ranging from 0 to 255. So now you can see through these three images, if this is 2 color data, you are only able to differentiate two types of features, one is appearing in black and one is appearing in white. If it is 16 colors data, then you can see you are able to discriminate various kind of features, but not in more details. But if you go with 256 colors, you can see the features are coming with more details. Now coming to temporal resolution, as I told to you that frequency with a satellite can revisit an area. Now as I have told to you about repeat cycle in satellite orbital characteristics slide. So repeat cycle means whenever our satellite is covering the same orbital path, like Earth is rotating, satellite is covering the same orbital path, that is called as repeat cycle. At that time also it is revisiting the same area. But revisiting is possible by satellite's instruments vision. It can tilt the sensor and it can see the same area. Suppose satellite is acquiring the data, after moving from this particular position, it had tilted the sensor and have seen the same area. So that is also revisiting of the same area, and it can provide also the temporal resolution data for the same area. So normally different types of application, what kind of temporal resolution data is required. So you can see for meteorological purposes, hourly need to monitor clouds are required. For oceanographic application, 2 to 3 days of repetitivity is required. For stereo viewing, 0 to 1 days of repetitivity, and for vegetation monitoring, 5 days of repetitivity is required. So you can see this two different season data of summer and spring, how the images are changing, how the features are changing. Now coming to various Earth observation satellites. So till now various satellites are launched from various remote sensing agencies, various space agencies by various countries. From Europe, France is taking care of Spot series satellite, European Space Agency is launching microwave series satellite, Middle East is taking care of Eros A and Eros B, North America is launching, from USA we are having Lancet series of satellite and even high spatial resolution satellites, which are your QuickBird and Iconos series of satellite. And then after we have Canada. From Canada we are having Landsat RadarSat series of satellite, they are actually microwave remote sensing satellite. And from Asia we are having Indian remote sensing series of satellite. We also have reset satellite, which is microwave remote sensing satellite. Then from Japan we are having ALOS satellite, which is having microwave as well as multispectral and panchromatic sensors. So these are some of the distribution agencies: spot imaging, miscellaneous image set. For in case of India, we are having National Remote Sensing Center, which are taking care of satellite data distribution. So as we know that first remote sensing satellite was ERTS, that is Earth Resource Technology Satellite, that was renamed as Landsat 1. So it is having a series of satellite Landsat 1, 2, 3 with having similar type of sensors, and you can see here this is having 912 kilometer altitude, and equator crossing time is daytime 8:50, 9:08 and 9:31. Now coming to a repeat coverage, this is having 18 days. So you can think of after 18 days it is able to cover the same orbital path. Then coming to adjacent orbit. Adjacent orbit is something like, suppose one orbital pass you had made, and after that after some days it is making the nearest pass to the first orbital pass, that is called as adjacent orbit. So after one day for Landsat 1, 2, 3 satellite it is making the adjacent pass, but for Landsat 4, 5 which is having the advancement in the sensor, that is having thematic mapper also, so it is taking around 16 days for repeat coverage and 7 days for adjacent orbit. So Landsat 4, 5 are having similar configuration. Landsat 6 have enhanced the sensor, that is ETM, but that failed just after the launch. Then Landsat 7 was launched with ETM plus sensor. The data sets for this particular sensors are freely available in Earth Explorer website, which is also called as USGS. From that you can download and you can use the satellite data sets. Landsat 8 was launched in 2013 with OLI and TIRS, that is operational land imager and thermal infrared sensor. So I am going to tell you the sensors details in my further slide. So these are some of the sensors. RBV is the return beam Vidicon with Landsat 1 and 2 and Landsat 3. So Landsat 1, 2 started with 80 meter spatial resolution, but Landsat 3 was having with 30 meter, and which is having multispectral scanner with 80 meter spatial resolution, which is having 4 spectral bands, green, red and 2 near infrared. And thematic mapper with Landsat 4, 5 is having 30 meter spatial resolution for 6 bands, and one is thermal band with 120 meter spatial resolution. Then Landsat sensors with ETM plus, that with Landsat 7 and with Landsat 8, you can see one panchromatic band was also included in ETM plus sensor, and you can see spatial resolution of thermal band is increased in that is 60 meter. And with operational land imager we are having 2 thermal infrared band and 2 more spectral bands are there, which is useful for atmospheric application, that is for cloud detection, that is Cirrus band, and one for your sea coast sea or your ocean studies, that is coastal blue band. Then spot satellites are launched. These sensors are having capability to tilt the sensor and can see the same area. So this is having capability to generate stereo data. So spot 1, 2, 3 spot series are launched with a high resolution vertical sensor, visible sensor, and for vegetation application spot 4, 5 are having that sensor. Recently spot 6 and spot 7 was launched with the purpose of making whole earth image data with very high spatial resolution. So this constellation was launched for that particular purpose. So these are the specification of your spots older sensors, that is spot 1, 2, 3 or 4, 5. So earlier this P mode means your panchromatic mode. So panchromatic mode, you can see this is your covering visible to near infrared. XS mode means your multispectral mode with 20 meter spatial resolution with 3 spectral bands. Now M mode means your monochromatic mode. Monochromatic mode means it is covering only one single band. In this particular case this is covering only red band. And multispectral mode for high resolution vertical infrared, that is covering 20 meter spatial, that is giving 20 meter spatial resolution data with 4 spectral bands. Now these are some more sensors of that. So P mode means panchromatic mode and super mode means 2.5 meter. Why it is written as super mode? Because this sensor is having capability to generate data with higher spatial resolution. So they are providing data with 5 meter, but after certain image processing they are able to provide data with 2.5 meter resolution. and this is for vegetation monitoring instrument with 1000 meter spatial resolution. This sensors are also available with spot series of satellite. Now we are having IRS series of series satellites. So IRS 1A 1B was launched with LIS 1 and LIS 2 sensor. We started with 72 meter spatial resolution data. Now we are having sensors that Cartosat 2C is also recently launched with less than 1 meter spatial resolution. So in 1995 and 1997 with 1C and 1D we are having panchromatic sensor with 5.8 meter spatial resolution. Then OceanSat was also launched in 1919 was launched in 1999 with ocean color monitor and multi scanning microwave radiometer. So these are actually useful for your oceanic application or coastal studies. Then Cartosat 1 was launched in 2005, which was able to give you stereo data with 2.5 meter spatial resolution. Then Cartosat 2A was launched with very high spatial resolution, less than 1 meter resolution. Then OceanSat 2 was launched in 2009 with ocean color monitor and scatterometer. Then Cartosat 2B was launched in 2010 with panchromatic sensor with 80 centimeter resolution. Then ResourceSat 2. So you can see in earlier slide ResourceSat 1 was launched in 2003 with LIS 3, LIS 4 and AWIF sensor. So this ResourceSat 1 and ResourceSat 2 are having similar sensors, but the difference was radiometric resolution. So spatial resolution are same for ResourceSat 1 and 2 for all the three sensors like LIS 4 5.8 meter, LIS 3 23.5 and AWIF 56 meter. Difference is only 10 bits radiometric resolution for LIS 4 and LIS 3 and 12 bit for AWIFs. Then Megatropics was launched with the collaboration with France. They have launched this particular sensor for monitoring the cloud. Then these are the specification of your IRS previous series. So I told to you it started with 72 meter resolution. Then panchromatic in IRS 1C 1Ds are having 6 meter spatial resolution. Then IRS sensor with LIS 4 that I told to you, LIS 4 and LIS 3 with ResourceSat 1 with 5.8 meter. Now you can see here it is 7 bit radiometric resolution. So more the radiometric resolution will be, you will be able to differentiate fine energy level recorded by the sensor. Then first commercial satellite was launched by US, that is Iconos, which was able to give near photograph quality of the earth's surface with 1 meter spatial resolution. So you can think of 1 meter spatial resolution we are getting now from space. So with 11 bit radiometric resolution, but swath width here you can see that is around 13 kilometer. So Landsat started with 80 meter spatial resolution with 185 kilometer swath, but here you can see it started with 1 meter and 4 meter for multispectral. Then QuickBird sensors data sets are there, that is 0.61 meter with nadir viewing, and off nadir means if you are able to tilt the sensor and you are seeing this area, then the spatial resolution is reduced to 0.72 meter. For multispectral it was 2.44 meter and off nadir it is 2.88 meters, and same spectral bands are there similar of your Iconos satellite. Then we are having Worldview 1, GeoEye 1, Worldview 2, Pleiades 1A 1B from different countries. So that is having 50 centimeter spatial resolution, and GeoEye 1 was at that time in 2000 means before launching of Worldview 3, it was having the highest spatial resolution, that is 41 centimeter resolution data. So the older spatial resolution was 41 centimeter, but due to some technical problem they have recently increased the altitude from 681 kilometers to 770 kilometers. So that's why the spatial resolution is getting got affected, and it is now 46 centimeter for panchromatic, and for multispectral now it increased from 1.56 meter to 1.84 meters. Then Worldview 2 was there with panchromatic sensor 46 centimeter and 1.84 meter spatial resolution for multispectral. So you can think of how much spatial details you are going to get from space. Then Korea multipurpose satellite was also there. So they are also having very high spatial resolution satellite data sets. So ComSat 3 are now having 0.7 meters for panchromatic, and for multispectral it is 2.8 meters. Then coming to Worldview 3, as I told you, this was launched in 2014, and that is having panchromatic sensor with 31 centimeter. So you can think of how much spatial detail you are getting from space. And for multispectral and SWIR bands and Kevis bands, for different kind of application, these are the spatial resolution. So for multispectral, you can see this is giving you 1.34 meter spatial resolution. Now meteorological satellites, as I told you, normally your geostationary satellites are useful for weather prediction and monitoring. So it is having advantage of global coverage at very high temporal resolution. So this is the advantage of your geostationary satellites. So various type of meteosats are there, that is NOAA series satellites. NOAA series satellites are actually near polar and sun synchronous. GOES and INSAT series satellites are in geostationary orbits. India has launched INSAT series of satellites which are useful for telecommunication and meteorological purposes. These are some of the data browsing websites. So this is earthexplorer.usgs.gov. From this you can download various data sets which are freely available of Landsat series and for other satellite sensors also freely through this website. From nrsc.gov.in you can place the satellite data order, and some data sets till list 3 which is having 23.5 meter resolution and AWIFS data with 58 meter resolution you can download through this particular website. So from Bhuvan you can download the data sets free of cost. So thank you.